Now, let's mention a very important and applied example of this chapter. Why do we need to dimensionalize or non-dimensionalize parameters, and how we can take advantage of those things? This is called as theory of models, which means that assume that there is a big problem. For example, the previous bridge problem that I have already explained. And what we have is, at the very end, we can write pi 1 is a function of the other pi terms, pi 2, pi 3. This is for the real problem. Now, let's call this a prototype or the principal model. In contrast to prototype, I can make a smaller model which is easier to deal with, which is easier to carry out any experiment on those things. And I want to call it model. So for this one, I would repeat this process as pi 1m is a function of pi 2m, pi 3m, and so forth. M here stands for model. So pi 1 is for the prototype, the real, the main structure, and pi m corresponds the model of the main one. To make sure that this model exactly behaves and predicts the behavior of the first one, prototype, all dimensionless corresponding dimensionless parameters should be identical. On the other word, pi 1 should be equal to pi 1m, pi 2 should be equal to pi 2m, and so on. So first, we need to form the pi terms. Then we need to make sure that pi terms, the corresponding pi terms, are identical between the prototype and its model. That's a great achievement. Why? Because, for example, sometimes it's very expensive or somehow difficult to conduct an experiment on the real prototype. Instead of that, we can create the associated model in the lab, but we expect to see the same results. Otherwise, it's useless. So to that end, we need to make sure that the corresponding pi terms are identical. As a good example, let's get back to the previous example and put it in another way, in a more complete, comprehensive way. The same example here, but all values are given. For example, the d value here is the d is 0.1 meter. H is 0.3 meter. Velocity is also given, which is 50 kilometer per hour. Kilometer per hour. And also, what I need to know is this. I need to find h of the model. This is the first of all. Secondly, I need to know the omega, the frequency of the prototype, because the frequency of the model is given here. Omega of model is given as 49.9 hertz. There is one thing very interesting about this example. This example means that there is a structure of the bridge with the true parameters, true dimensions. It is exposed to the air, ambient air, with the 50 kilometers per hour. But for the model, instead of the air, I want to put the model in air, so in water. So model in water rather than air. So I want to use a water tunnel rather than a wind tunnel in the lab, which is less expensive, much less expensive than the wind tunnel. And when I carry out the experiment in the lab for the model, I can measure the frequency of the model with this word, with this value. But now I want to see what happens to the real prototype in terms of the frequency. So find this thing and these things. I have already found pi 1, pi 2, and pi 3. So for this example, for example, get back to this, pi 1 is d over h. Therefore, I would say d of model divided by h of model is d of prototype divided by h of prototype. So this is pi 1, this is pi 1m, this is pi 1. Therefore, I can find h of model from this equation, which is h of model is h times d model divided by d. Everything is given. D model divided by d. But when I want to solve this, I will notice that I still need to find d of model, which is not known. So I need to take advantage of the second one. Pi 2 is Reynolds number. Therefore, I would say that rho model, V model, D model divided by mu model is equal to rho Vd divided by mu. The other one. So for this case, if you see, this is pi model, pi 2 model, this is pi 2. For this case, we still need to know d of model. I believe it should be given in the problem. Yes, d of model is here. D of model is also given 20 millimeter. So I have these two, and d of model is given 20 millimeter. So if I solve this very simple equation, I can find h of model as 60 millimeter. And then when I have h of model, I still can use this equation to find d of model. So solve it for d of model. Remember, these two terms for the model can be obtained from water, and these two terms are known from air values. Also, d is given, which is 0.1 meter. V is given, this value, but you need to convert it into meter per second. dm, I just found it, 60 millimeter. Therefore, I can solve it instead of dm. Now I can solve it for Vm. Vm is gonna be 4.79 meter per second. Then the problem asks you for omega. omega is the third one. So if I want to continue this table, I would say that, for example, P3 is equal to P3m. Therefore, pi 3 is a Strouhal number. And I can say that a Strouhal number, omega d divided by v for the prototype is omega model d model divided by v model. D model, let's use this color. D model is given 20 millimeter. V model, I have just found it. That's V model. Omega of the model is given. D is the real D value, which is 0.1. V is the real velocity, which is still given. Then you can solve for omega. And therefore, omega would be 29 hertz. If I want to summarize this example, a real problem is given in the air. I want to model it in the lab into the water instead of the air. I need to know the dimension of the model, and then also I need to find the frequency of the real problem. I could take advantage of the theory of models, and Pi-Buckingham theorem has already been employed where I predefine pi 1, pi 2, and pi 3. I hope this lecture helps you to understand the concept of dimensionless parameters and how you can apply them into some problems. Thank you.